Well, good afternoon. Welcome to our conservation webinar series. I'm Liz Ripley, the Conservation and Cover Crop Outreach Specialist with the Iowa Learning Farms. I'd like to welcome you all today as we dive into using corn cobs to improve nitrate removal in bioreactors. We have with us now Dr. Taylor Vroman from Iowa State University and Data Solutions Analyst at Ag Outcomes, talking about some of her work through her PhD program. If you have questions at any time for Dr. Vroman, please feel free to enter those into the chat. We will get to that Q&A session following her presentation. So with that, the virtual floor is all yours.
Awesome. Thank you so much for that introduction, Liz. Like she said, I'm Taylor Vroman. I just, as of less than a week ago, graduated from Iowa State with my PhD in environmental science. So the doctor introduction is a little funny to me still. But I worked under Dr. Michelle Sapir, working on denitrifying bioreactors. I just started my new role at Ag Outcomes, which is a subsidiary of Iowa Soybean Association, as a data solutions analyst. But today I'm going to be talking about the research that I did during my time at Iowa State. I'm excited to get started. So first, just to give you a little bit of an outline of what to expect today, I'm going to be talking about how bioreactors work, what the landscape in Iowa with bioreactors currently looks like, how can we improve the efficiency of them, what about greenhouse gas production, and then finally talking about just the overall feasibility of using corn cobs and funding opportunities. So first, I know a lot of us might be familiar with tile drainage bioreactors, but I wanted to give just a quick overview here. So if we're looking at this diagram of a bioreactor, working from left to right, I think I got my laser pointer up here, we can see our agricultural field on the left with our tile drainage running underneath the surface. And typically, this tile would directly dump into nearby surface water, but instead, with a bioreactor, we can direct it into an underground trench filled with a carbon source that's typically wood chips. And what happens underground is that bacteria can utilize excess carbon in wood chips to reduce nitrate in the water to a harmless nitrogen gas. And now nitrogen gas makes about 78% of our Earth's atmosphere, so we know it's totally harmless. But the microbes are really using that carbon source, which is a lot that we'll be talking about today. If you haven't seen a real bioreactor, there's one being installed in the upper right-hand corner. We like to say that they're roughly the size of a school bus. You can see that it's partially filled with wood chips. Before construction, there would be more added and then topped with a foot or two of soil. And so overall, they're an edge of field practice, and they work to remove the nitrate in the drainage water and convert it to the harmless nitrogen gas. And so what does bioreactor usage look like across Iowa, and why do we need them? Well, we know that the Iowa nutrient reduction strategy is calling for a 45% reduction in nutrient loss. And bioreactors are an effective tool that can help us reach this goal. And so across Iowa, we currently have about 300 bioreactors, give or take. Now, there's a calculation that's been done that says that in order to reach the Iowa nutrient reduction strategy goal of 45% low nitrogen reduction, we need over 100,000 bioreactors, which means that we're at less than 1% of the required bioreactors that have been installed right now. And so this, to me, as a researcher, means that we need to ensure that the bioreactors that are installed are absolutely as efficient as possible. And so with this calculation, we are using the old average percentage removal of nitrate at 43%. So when this calculation was done, this number has since been dropped, which really reinforces the point that we need to make these as efficient as possible. But this made me question, how does improving the efficiency impact the number of bioreactors needed to reach that 45% reduction? And so this 43%, again, that's the average that we used of all the nitrate going in from the tile drainage. We're able to remove not quite half of it. And so again, just assuming that 100,000 bioreactor number, if we are able to improve the average efficiency just by 7%, we dropped the number of bioreactors needed by 14,000. And we can see that trend continue all the way up to a very generous 80% average removal would about cut the number needed in half. And I'm not saying that we're anywhere near that 50,000 number, but I am saying that in terms of thousands of bioreactors, we're able to drop nearly half, which is a huge deal. And so here are these numbers again. This was a previous reduction when this was done at 43%. And now you can see the updated iron nutrient reduction strategy assumes a 24% reduction in bioreactors, which makes improving it even more impactful. And so if you were able to watch the webinar a couple weeks ago, you would have seen another presentation on bioreactors, but focusing on different species of wood chips used to improve the efficiency. Today, I'm going to be talking about corncobs, as you're probably well aware of by now, and just looking at it as a totally different carbon source and as an opportunity because we think we have that available here in Iowa. And so we know already that carbon in corncobs is more available than in wood chips. Now, what does that mean? When I think of carbon availability in corncobs, I like to think about it like the sugar in Fun Dip. I don't know if you've had Fun Dip. I had it a lot as a kid, but it dissolves very easily in your mouth. You get the sugar rush very quickly. It's very absorbent and dissolves right away. You don't have to put any work in. And that's how I think about the carbon in the corn cob versus in a wood chip. It's more like a sucker. You have to suck on it for a long time in order to get the sugar to actually release. It's a lot slower to work. And so that's kind of how I think about the carbon in these two media types. But this inevitably raises the question of, okay, great. So does the carbon just run out quickly and how long can corn cobs last? Well, we're very interested in this question, and the site or the lab that I was a part of at Iowa State had a pilot scale location of bioreactors, and so a little bit smaller than field scale. But we had 9 different bioreactors with 3 different ratios of corn cobs to wood chips. So I'm going to show you a figure here. I'm looking at the colors and explaining what that means. Our gray bars is 0% corn cob, 100% wood chip. So that's representing our traditional bioreactor fill material. And then our red bar is showing a bioreactor with 25% corn cob, 75% wood chip. And then our yellow bar is showing us the highest proportion of corn cob at 75% to 25% wood chip. And so we can see that we have data from 2019 to 2025. And in both years, our bioreactors with the highest proportion of corn cobs actually outperforms that of wood chips. And we see that through time after 6 years as well. And sure, the performance has dropped, but we see that consistent trend both when it was first implemented and installed and 6 years later. Our lab actually has some sites going out now, field scale, that are 100% corn cobs. And the longevity of these systems is something that we're super interested in and are really hoping to get some good data for. And so now talking about, we know we need to improve the systems. We think corn cobs are a good option. My work was looking at corn cobs versus wood chips in a lab scale bioreactor at various flow rates. Why is various flow rates important? Well, in the field, we're not able to directly, really consistently control the volume of water that's entering a bioreactor because it does treat tile drainage. It's really dependent on the precipitation around the time of year, etc. And we talk about flow rates in terms of hydraulic residence time, which I'll be talking about today as HRT, and it's essentially how long the water is in the system. So to walk you through the methods here, again, I used a controlled lab scale column approach. So think of these as mini bioreactors. For reference, these are about 2 feet tall and 8 inches across. I had 3 of them packed with mixed hardwood wood chips, and then 3 of them were filled with corn cob segments Typically in field bioreactors, we don't cut up the corn cob in any sort of way. But for this project, we cut them down to about 1 to 3 inch sections just so they would pack better in a small area. And so we ran a synthetic nutrient solution through these columns, starting at the gray tub here. So this is filled with a solution that has 30 milligrams per liter of nitrate, which is a value that we see pretty standardly in some tile drainage. And then we'll work it up through a pump, the water removed from the bottom to the top of the column, then out through this effluent tube. When I'm explaining this, a question that I get quite a bit is if it's an open or closed system. It's open, so these bioreactors are always treating water that has 30 milligrams per liter of nitrate. And so looking at the pump here, I ran these at 3 different flow rates, 4-hour, 8-hour, and 16-hour. And so again, remembering that HRT is how long the water's in the system, our 4 hours moving really quickly. This would be representative of field conditions after an extreme precipitation event. We have a lot of drainage moving through the system. Our 8-hour is ideal. That's what we want. We've seen really good nitrate removal efficiencies at that, and we've seen really low greenhouse gas production. And then our 16-hour is when the water's moving really slow. So during any low flow drought periods. And so we took water samples weekly at an 8-hour HRT, and those are the acronyms I'll be using throughout today. We sampled nitrate, nitrite, total organic carbon, but I'll be talking mostly, obviously, about nitrate today. And we collected water samples as the water was leaving in these clear tubes here. So as it's actively dripping out, and here's kind of a peek into the columns of what's going on behind all the PVC. Okay, and so now we'll get into a bit of the exciting part here, the results. On the left-hand side, I'm going to have all my corncob data. On the right-hand side is going to be the wood chips. You can see the flow rates are at the bottom. I'm going to be moving from really fast flow rate to slow from left to right. And we have our nitrate removal efficiency in terms of percent there. And so looking at our corn cobs, we can very quickly see that we're able to reduce a lot of nitrate and that we're able to reach higher nitrate removal efficiencies at slower flow rates. And this makes sense because if we're thinking about how that bioreactor works, what this really means is that the microbes doing the work have a longer period of time to use the carbon to reduce nitrate. And so the longer the water's in the system, the longer time it has a chance to really work and really do its job. And so at wood chips, we see a lot lower nitrate removal efficiencies. We do see highest at 16-hour, but our second highest is 4-hour, which really isn't that different from the 8-hour. And so obviously we can see that the corn cobs are very clearly outperforming the wood chips, and now we're able to achieve really high rates at both the 8 and 16-hour. But something with talking about nitrate removal in bioreactors, we often talk about performance in terms of both percentage removal and load removal. And I feel like we don't ever really stop and talk about what that means very much. So I'm going to take a couple minutes to walk us through just an example of how we communicate that. And so we have a hypothetical situation here. 2 different systems, both achieving a 50% nitrate removal efficiency, which is what our last data was reported in. I want to say that we have a concentration of 30 milligrams per liter going in for both, 15 going out. So both are achieving that 50% removal. However, the difference is that the system on the left, I'm going to say, has an HRT of 8 hours. It has slower flow than the system on the right that has an HRT of 4 hours. And so in this same amount of time, I'm able to treat twice as much water at the 4-hour HRT than at the 8-hour. And so both my systems are achieving 50% removal, but at 4-hour, water is moving twice as fast. I'm treating twice as much water and removing twice as much nitrate. So to put some hard numbers to it, In an 8-hour time period, on the left-hand side, assuming that these systems are 1 liter, just to make it easy, I'm going to have 30 milligrams of nitrate going in, and I'm going to be able to remove 15 milligrams of nitrate at that 50% removal. But at 4 hours HRT, in an 8-hour time period, I'm going to have a total of 60 milligrams of nitrate going in and 30 milligrams of nitrate going out. And so I just said a lot of numbers, but the big takeaway here is that at the same removal percentage, at my faster flow rates, I'm treating more water, so I'm treating more nitrate. And so now I'm going to show us the same data as before, but in terms of load removal. So again, our corn cobs on the left, our wood chips on the right. So we see similar trends with our lowest at the really fast flow rate here, but we see that our 8-hour kind of surpasses the 16-hour flow rate. And then at wood chips, we can see that at 4-hour, our fast flow rate, we're able to remove more nitrate than at the slower rates. And so I have a couple really interesting thoughts on this. The first is that if I'm looking at just my corn cobs, my worst performance is at 4-hour. But if I'm looking at my wood chips, my best performance is at 4-hour. And these are statistically not different. And so what this tells me is that if we're only using wood chips in bioreactors, we're missing out on a lot of opportunity to remove higher loads of nitrate. And secondly, my corn cobs are achieving really high nitrate rate removal rates at both 8 and 16-hour. And so that tells me that my window of opportunity, kind of the sweet spot for peak nitrate removal in corn cobs, is wider than that at wood chips, and that this is a little bit more limited in the field conditions where it's going to really do its best. And so I'm going to talk just very briefly about why this could be. And these are things that we already know and that should be happening, but it's always nice to get some data to back that up. And so here I'm looking at a figure of my total organic carbon on the X and then my nitrate removal percentage efficiency on the Y. My corn cobs are shown in a yellow color, my wood chips are in blue. And so I can see that my corn cobs have a much higher range of carbon availability than my wood chips, and that as I'm adding more carbon, I'm directly able to remove more nitrate. So corn cobs do have that more available carbon for microbes to use as fuel for nitrate removal. And so this kind of goes back to my fun dip versus my sucker analogy here. My corn cobs have a lot of that sugar carbon available to use to, instead of reaching a sugar rush, to reduce more nitrate. Okay, so that was a lot about nitrate. But now I'm going to kind of shift to another question that I get quite a bit, which is all about greenhouse gas production. When we're implementing these practices, we want to make sure that they're very positively impactful and as efficient as possible. And so we did also measure greenhouse gas in the column projects, and we measured for methane, nitrous oxide, and carbon dioxide. But we saw really low numbers across all flow rates, across both wood chip and corn cob. But we do have to remember that it is in a lab scale. It's basically a mini bioreactor, right? And so I want to share some data from a different research site. I'm kind of moving quickly here, but I'll give you some background into what this site is. But now I want you to think in terms of big field scale, back to that school bus size bioreactor. And so a little bit about this location. It's a dual chamber bioreactor, which means that we were expecting to treat a lot of water, and so much so that we put 2 bioreactors running parallel to each other. And so we have 2 different bioreactors in one pretty much. It was installed in the summer of 2018. And what's interesting for this one is that we have internal monitoring wells shown by those red dots along the length. So that means that we're able to look at gas production within the bioreactor and not just at the inlet and outlet. And so this is a top-down view of the bioreactor with our water coming from the tile drainage down here. And then we can see our flow arrow is going to move from the bottom up for both of these. And so we have monitoring data from 2019 to 2024, including greenhouse gas, including nitrate. We actually have a suite of other water quality parameters we measured, but this is what I'm going to be talking about today. We sampled about weekly from spring to late summer. Okay, and so before I flash a bunch of data on the screen here, I'll tell you about what you're about to see. And so this is going to be data from 2024 from the first chamber, if you remember one of the bioreactors, because we have two here. First, I'll be showing you the water quality data, just nitrate. And we're going to be looking again, top-down view of the bioreactor, width here, length there. And so we can see everything is pretty much as we would expect it to see or expect it to be. And so we see nitrate right at the beginning, right off from that tile drainage, and it's reduced really quickly. And so this is okay. And just as a side note here, I was very strict with my smiley faces. So it's great that we're removing nitrate, but ideally we wouldn't remove it all right away, which we'll see why when we look at the methane data. Our nitrous oxide looks really good. We don't really see any hot spots or anything. We see really low production. But this is an important thing to keep in mind and to keep monitoring because it does have such a high global warming potential. And so now we're looking at methane. We can see if we look really at the first and third figure here, as our nitrate is reduced, then we start moving down the redox and we start to see some methane production. To give you some context, these values are really, really low. But again, I'm being strict with my smiley faces here. But just with the trend, it's something that we should really keep monitoring for. And so next, I'm going to show you the next chamber. Our first figure looks very similar. But interestingly, in our nitrous oxide, we do see a bit of a hot spot. We think that this is because of some weird flow situation, that something is moving really quickly. But a really big positive is that we're able to see it be removed along the length. And by the time that the water is exiting the system, that concentration is really low, which is a really big positive. We see similar trends in the methane here. As soon as our nitrate is reduced, we're able to see some production, which again, very strict. These values are really low. And something to keep in mind is that when we talk about gas and bioreactors, we're typically talking about it in a dissolved form. And so that means that you're actually taking a water sample and looking at the gas within the water. And that as this water is released into a nearby stream or creek, in this case, Big Creek, there's going to be further nutrient cycling that goes on, and it's probably not going to stay in that form. I took this code from Lindsay Hartfield, who monitored this project, and I believe presented on this a couple of years ago on the same exact site. And she did a calculation in terms of total carbon dioxide equivalent of greenhouse gas at this site. And her emissions were actually a bit higher than these in the earlier years. And found that there is a less than a 1% carbon dioxide equivalent increase in emissions expressed over the drainage area. And so I know these numbers, like this looks a little bit alarming, but contextually it's very, very minimal, which is a huge positive. Okay, and so we've established that corncobs work well. We see that in the lab scope project, we saw really low gas emissions. So why don't we have corncobs everywhere? I took a snip from a blog from the Iowa Learning Farms website that featured my professor, Dr. Michelle Sapir, that I worked under, talking a lot more. I encourage you to go check it out about using corncobs in bioreactors. And a key takeaway is that right now we're sourcing all of our corncobs from green products in Iowa. But right now, somehow, despite looking around all the corncobs we have around us, there aren't enough cobs produced by seed corn facilities to meet the demands and to serve as a source. And so we know that they perform well, but actually sourcing them and getting them into a bioreactor remains to be a limiting factor. And just very briefly about funding opportunities. Um, if you just do a quick Google of bioreactor funding sources near me, you have a lot of opportunities that show up. I took a snip of just a couple by the Story County Soil Water Conservation District, showing that the batch and build provides 100% funding to landowners. Here's another snip from the Iowa Agriculture Water Alliance website, talking about checking with your USDA service center and that there's a lot of cost share options. Right now, there are so many opportunities to get these 100% funded, and it's not always going to be that way, which is why I think it's a great time to be asking questions and to be learning more about these practices. And so, rounding it out here, I believe we're just right on time. Some key takeaways. The science shows that corn cobs are a viable option for bioreactors to replace wood chips. We see that they outperform wood chips in both nitrate removal, percent removal, and load, and that replacing wood chips with corn cobs improves the overall efficiency, which could help decrease the number of bioreactors needed to achieve nutrient reduction goals. We consistently see minimal greenhouse gas production. However, the corn cob sourcing remains an issue, and that funding opportunities are available. And if you are interested, it depends a lot geographically, and I encourage you to reach out to your local agencies. And with that, I believe I will take some, not questions. I'm going to move on to here now for Liz to take over.
Excellent. So thank you, Dr. Vroman. That was excellent. I put a couple links in the chat if people wanted to check out one, the virtual field day that she referred to, which is on our YouTube channel, and also the blog that Dr. Sapir posted earlier this year. So you can check those links out in the chat. If you attended today to earn a CCA CEU, please be sure that you email Elena Whitaker at alenaw@iastate.edu by 5 p.m. today with the following information noted on the slide so that we can get the credit submitted on your behalf. So go ahead and go to the next one, please. Yes, so our voluntary demographic survey. As a USDA funded program, we do encourage our participants to complete this demographic survey. It takes just a couple minutes to do. If you've already done for 2026, thank you. Only one response is needed. If you have not, you can either scan that QR code. It's fairly easy to do on your phone as it is a short survey, or you can type in that URL, iowalearningfarms.org/survey. All right, moving along here. Our next presentation will be with Dana Kolpin, is a research hydrologist with the U.S. Geological Survey, and talking PFAS in agriculture, research by the Food Resources Lifecycle Integrated Science Team. So if you're interested about those forever chemicals and their connection to agriculture, please join us next Wednesday to learn more about that. And then our last slide here before we get to questions is... Oh, that's okay. It's all about where you can find our webinars. And so go ahead and you can, yeah, if folks have specific questions, we can maybe go back. But you can find them on our website. Simply search iowalearningfarms.org. We have all of our webinars archived there. We've also set up a YouTube channel so you can search by year and topic. So if you're looking for more on bioreactors and edge of field practices, that YouTube channel is really helpful for that. All right. There have been a lot of questions and they keep coming in, so I'll try and keep up. I think you maybe touched on this just a little bit, but as of right now in the size and design of these bioreactors, about how many acres are we talking about being treated by a single bioreactor?
Yeah, so we usually say between 90 to 120 acres for one bioreactor. I know for the research for the field site that I talked about, we had two. And so that's obviously able to treat a lot more acres, but to take about the same amount of land out of production. But roughly between 90 and 120 is a range we like to say.
And for that first site where you talked about it was a mix of corn cobs and wood chips, how were they mixed at the field site?
Yeah, so I guess I should explain this a little bit better. They were not mixed together, but instead we had sections of, I believe it was the corn cobs were in the first 25%, and then the 75% after is all wood chips. And I know there's a diagram of this exact field site on the blog as well, that shows that a lot more clearly. But they weren't mixed together, they were kind of sectioned out along the length of the system.
And so you talked about your flow rates for your lab trials. So looking field scale, how effective is a bioreactor for like 12-inch tiles? And then they're specifically mentioning like surface tile intakes. My understanding is surface tile intakes aren't necessarily something that's encouraged for use of a bioreactor. Do you want to elaborate on that a little bit?
Yeah, and so if I'm understanding this correctly, it might have been somebody that heard me present another time that one of our field sites actually we did pump in surface water from a creek. Is that what we're?
I think they're just asking because some of these tile systems are quite large, is I think what they're
Mhm.
concerned about in terms of being able to process that flow. And I think in your early diagram too, as well, there is a bypass. So we're not
Yes.
talking about treating 100% of the water. Um, but are surface intakes still a challenge from a sedimentation concern?
Yes, to both of those. Yeah. First, they're all bioreactors have a bypass. We would never want to not have a bypass and put too much water in, and back up water in a field. We're very aware of that. And so, yeah, if we had a high flow event, high precipitation event, we would rather bypass that water straight into the nearby stream, rather than having any negative impacts. And second, yeah, in one of our field sites, or in my experiences at Iowa State, we did have a surface intake, and we found that there was a lot of compaction, and a lot of clogging issues, because of the sedimentation. I could talk for a while about that. And if you have any more questions, I'm happy to talk more and to email me with that, because that's a whole nother conversation.
Maybe it's a
But
whole
it is
other
a
webinar to have you back for. Uh, so there's a
challenge.
couple of questions actually asking about longevity. So
Mhm.
comparing corn cobs to wood chips and kind of how that may impact how long these systems last.
Yeah, this is a great question, one that there's not a black and white answer to. I will say that from what we've seen, we've been surprised, at how long the corn cobs are performing for. I actually just saw a paper yesterday on LinkedIn. I wish I could remember the author, but there was another lab scale project, that was looking at the performance of corn cobs, barley, wood chip through time. And they also saw that corn cobs are lasting longer than we think. But this is a question that we're not going to be able to have the answer to until we see it in the field. Which is why I believe that, we have these 100% corn cob systems going out now. We're going to see how they last through time. We are able to take samples out and look at the carbon availability, years down the line as well. But so far, even looking at this, I mean, even our wood chips, in that gray, our 100% wood chips, their performance is going to decrease through time. That's just how it happens. That's just how it works. But we are seeing very similar rates of decrease in the corn cobs as well. So it's a really good question.
So a couple questions here. I'm going to group them together. So the
Okay.
first part of the question is why can't non-seed corn cobs be used? And maybe the second question of the tool to harvest maybe non-seed corn cobs.
Yeah, that's kind of a loaded question because, looking around, like you have we have corn cobs everywhere. Why can't we just dump it into a bioreactor? And we actually did that at one site. There's a Vermeer tool, I believe. I don't know the exact name of it. It's not made anymore. We were able to pick up cobs, and they had one of those, and they were able, and I believe they got funding for using their own corn cobs, in a bioreactor. Um, but right now, Green Products is the sole, producer, um, and so that's just kind of how it is right now. As far as non-seed, I'm not really sure how to further answer that question, but
Yeah, so essentially, when we harvest corn here in Iowa, we harvest the whole ear. And then it's
mhm.
the corn is stripped from the ear at the processing facility. So we get these clean corn cobs like you have pictured there. But obviously out in the crop fields, the machine's doing the whole thing. We end up with just the seed and the hopper, and then there's mechanisms within the combine that size that residue and then fans that blow it out the back. And so we are working, Taylor referred to a project where they were harvesting their own corn cobs as they combined their field. And we're actually going to be hosting a virtual field day on that particular site later this winter. So we wanted to get some data collection to see how it's performing before we hosted that event. But it's a pretty unique system. As Taylor mentioned, the machinery itself is discontinued, but it's like a pull along piece of equipment behind the combine that was capturing those corn cobs to be utilized. Because you're right, we grow a lot of corn. We got a lot of potential corn cobs out there, but our current harvest machinery doesn't necessarily provide them in the form that we would need to fill a bioreactor. Um, so there's a question here, kind of maybe longer term as we do these pilot scale full corn cob. How close is this being allowed by the technical standards for these practices?
Yeah, and so actually to use corn cobs in a bioreactor, we didn't even have to get a variance on the standard. Um, because of the carbon material. And this kind of addresses the last question as well, is that there are a lot of standards in the amount of residue and like the extra things that are in wood chips. You can't have a lot of just like leafy material, anything like that. And that kind of goes with corn cobs as well. If you were to include other pieces of the cob, we know that that could result in a lot of clogging issues. And so that kind of answers the last question. But this one, yeah, we didn't have to get any sort of variance because it already met the standard and was approved as is.
So going back to, I think there you had a chart about the available carbon in corn cobs. They're asking, why do corn cobs have more available carbon? And does it have something to do with that C to N ratio?
Yeah, that's a good question. I mean, if we think about the physical structure of think of a soggy corn cob. It's soggy, right? Like that's what comes to mind. It's going to break down very quickly. Versus a soggy wood chip isn't quite as gross and soppy sounding. And we know that the C to N ratio is a big part of the story. It's not all of it because wood chips also have that really high C to N ratio. We know that they're going to release that carbon and that it's there. But it's more in the type of carbon, I would say, as well. This is like they both have carbon, we know that, but there's actually a different. I encourage you to look up. We like to call it labile carbon, which is just that availability. So just because two different things have carbon, you might not be the microbes not be might not be able to actually access it in the same way, if that makes sense.
There's a question here, and I'm not sure if you've yet tested this, but as we think about efficiency potentially being increased with the use of corn cobs, could then the footprint, the bioreactor itself potentially be reduced with the use of corn cobs?
Like the physical size of the bioreactor, is that what
Right. If we can
means?
get similar efficiencies from a fewer, a smaller footprint of corn cobs than a footprint of wood chips.
That's a really interesting question. I will say I know, first of all, wood chip bioreactors take out a very small amount of land as is. And a lot of the times they're designed towards the amount of drainage area you're treating and not necessarily for you have the water has to be able to move through it in a certain size so we're not getting if we had really too small of a system and we're putting a lot of water in the water's not going to move slowly so a lot of times it's based on the water that's being drained but I can see that if we're able to reach high removal efficiencies and we didn't have to be so specific about the HRT because we're seeing high performance across a range. don't quote me on this anywhere, but I could definitely see that as something that should be explored and could maybe be a possibility.
So there was a question about the standard for NRCS bioreactors. So I put that in the link there. It does explain that the carbon source does not have to be wood chips, but has to meet certain standards
Perfect.
of how long it'll last and its ability to like be porous and things.
Mhm.
Um, let's see. There was one about like inoculating.
Yeah, for the columns, I assume,
Yeah, yeah.
probably.
Do you
Yeah,
need to
I should have.
inoculate?
Yeah, we did inoculate them. I'll go just in case. For these, we didn't just start with a nutrient solution. We actually grabbed tile water up from Big Creek, or no, not from Big Creek, from Black Hawk Lake, that we know has about similar concentrations, and we let it sit in there for about a week. And that's just so the microbiome could establish.
And
That's a good question.
maybe as the next steps as we get closer to these pilot stages being evaluated, the cost comparison for these systems when using corn cobs versus wood chips.
Yeah. So there's a paper I encourage you to look up by law of 2023 that did a cost benefit analysis of this this field site that reports it in terms of cost um, per mass of nitrate removed, and it shows that per nitrate removed, corn cobs were cheaper. I think there's a lot of it depends on the actual cost of the cob, depending on transport, depending on volume. But per nitrate moved, the corn cobs were shown to be cheaper in that paper.
I was trying to see if I could find that paper.
Yeah, it's GL Law 2023. Um,
Found it. I'll get it
Perfect.
shared into the link for or into the chat for folks.
Thank
Um,
you.
but yes, if you are watching this archive, you can also find it by simply Googling that. Um, it looks like it was published in Science Direct for the Journal of Environmental Management. Uh, okay, let's see. I think there was one or two other questions in here. Does the degree of lignitation determine how long the cobs will last?
I would assume yes. I don't have a but I haven't done anything. I don't think that gives a good answer to that, but I would assume so.
Excellent. Well, that's okay. But I'm sure you'll be working on publishing more papers out of this research as well from Dr. Sapir's lab. And there's ongoing research looking at corn cobs, as she mentioned, both full scale and also examining how wood chip species could factor into performance for the wood chips as well. So keep in touch with us at the Iowa Learning Farms. We'll be sharing results as those research projects move forward. And we thank Dr. Vroman, I'm still going to keep saying it, for joining us today for this excellent webinar. We thank you and thank you all for tuning in today. Have a great afternoon.